Okay, let's start the last session for today. And I've been asked to tell something about the device tree and the experiences, how it works, what it is. And I have prepared some demonstrations so that I can show here some details so you just can lean back and listen. It's not a workshop, it's more training or let's say an explanation of what all the device tree is. So I thought to start the presentation just with the questions that come immediately. What is the motivation of a device tree within Linux? Where does it come from? And how should it be used in an ideal world? Yeah, the motivation is that a kernel, like Linux, needs a lot of hardware-specific configurations for drivers. Every piece of hardware is different. And the interaction of these devices and drivers somehow needs to be specified. In the past, this was done with so-called board files, so that every board did have a special C code board file that defined, well, I am a GJ04 board, for the name. I have this type of display to control, and so on. And this was all made by code, which is not bad in itself, but it became very difficult to maintain. And the key problem with these board files was that every board file was completely different from every other, so there were no synergies between the board files, even if they have the same CPU. There had been dynamic aspects inside, so the additional drivers or hooks and callbacks and such things did appear in the board file. Sometimes the board file did try to find out on which specific board variant it is running on to initialize different things. So board files became a nightmare for the Linux maintainers, and at some time Linus said, well, that's a mess, you have to resolve that. And then the device tree was introduced for ARM processors. It is a static description of the hardware instead of some dynamic initialization by this board file code. And there's another mechanism to configure the device, that are the boot arguments, that the bootloader knows on which board it is running and then tells the kernel some configuration. But the boot arguments, they are also not easy to handle. There's no standard for that. Which boot arguments exist, what the meaning is, and each driver could define its own set of boot arguments, and this was also quite confusing. And they have own syntax sometimes. Yeah, really interesting paragraph. So each driver introduced its parser for special boot arguments to do their things. Yeah, something about the history. Well, that's my interpretation. I have not checked everything, so that's my current view of history. It was invented a long time ago as part of the open firmware, which was developed by Sun, Apple, Spark, and used for Spark and PowerPC systems. Basically, the device tree is a data language like XML, JSON, or next step property lists. Into Linux, it was already introduced for PowerPC some years ago, and that was mainly a reason why Linus said, well, look at these guys at PowerPC, they have solved that. ARM guys, look there, how it should be done. And from that on, which was the 3.14 kernel, it became more or less mandatory. So they do not accept drivers that do not support a device tree. Yeah, the ideals, it should be static. So there should be no dynamic component inside. It should only describe hardware or hardware variants. So it should not be a replacement for the kernel configuration file. The kernel configuration tells what you want to have compiled into the kernel, what you want to have as modules, and some configuration options. You can change the size of caches and so on. But that's not part of the device tree, and vice versa. And goal is that it should be independent from Linux. So it should not be a Linux device tree, but it should be a device tree that describes the hardware, so that this description is open to any operating system. That's the goal. At the moment it isn't completely, in some aspects it is, in others it isn't, but that's something the device tree maintainers and policy makers keep in mind.
Are other three operating systems already using device tree lookalikes, or?
I will have an example at the end. A very small one, but yeah. So this was the general overview of the device tree, what it is good for, why it is there, and now let's look into it as a language, as a programming or data description language. How does it look like? What is the structure? What is the syntax? These are the most important questions. The first thing to know is there are two different formats, a source format and a flattened device tree. Basically, it's source code and compiled binary. The flattened device format is just one binary file. They differ by the standard file extension, which is .dts, device tree source, and DTB, the device tree binary. The source code is, of course, human readable, which is sort of a standard defined by this open firmware. There's an include mechanism, the DTSI, which helps to modularize these device trees, something I mentioned with the board files, which did not happen, that two very similar boards did not share code of the board file. Here with the device tree it can be done. And the compiler is of course doing a syntax check. The binary is compiled through the device tree compiler, which is either part of the kernel tool. So if you git clone a kernel tree, you will have the compiler included in that kernel tree in the, I think, script something. Or some distributions have it as a separate package. Yeah, the drivers inside the kernel, they can load this device tree for the board they are running on by using some OF, Open Firmware API, within the kernel. So the driver can read through this data. There's also a mechanism within U-boot. U-boot can also read and even modify these device trees, which is, well, bringing back some of the dynamics of the board files, which I did mention that there might be small variations of boards. For example, between the GTA03 and 04, we have changed some GPIOs. So basically, the U-boot could know, well, I am running on an A3 board, or I am running on an A4 board, and depending on that, modify the device tree. But there's a different mechanism that is, in my view, even easier to handle than having to modify that. That is just to have two different device tree binaries and have the U-boot load either one. A final note, very rarely known, so it's, I remember that it exists, and yesterday I researched, it took me 15 minutes to find out again how it is named. There's a device tree decompiler or FTD dump tool, for example within Debian, which allows to print a DTB file in the format of the source code. So you can look inside some device tree binary, how it is organized.
It's also possible with device tree compiler, you just define the input file is binary and output will be binary and create a better source file.
Oh, okay. So
you do it vice versa from
yes.
non-binary to binary and from binary
the device tree compiler makes source to binary, and this FTD dump does.
No, it can just if you switch the format, you can do it the opposite way.
Yeah.
Okay.
It's
like the DD. You say output file, input file. If you change it.
Yeah. Okay.
Yeah.
Now, the device tree concept. The concept is a tree of device tree nodes, and the nodes, they have a label, a name, and properties, and they can have subnodes. So this forms a tree of these data structures. There's a root node, and that has to be defined in the device tree system. Now let's go to the syntax. Okay, it should be readable. The syntax is that there's an optional label, then a colon, and the name of the tree, then curly braces, and a semicolon. So to some extent it resembles the C block structure. Then it has properties, either properties with value, with an equal sign, but there are also properties that where you just define their existence, but no value, and this device tree API in the kernel can check if that property exists or does not exist. So you don't have to always say value property is true or property is false. You just define the property or don't define. And then you just pack in subnodes. Subnode label is optional again, the subnode name, and then curly braces, and the same goes down. So this is the basic syntax. There's a root node, and like any node, it is just written, or the node name is a slash, and the device tree compiler knows then that it is a root node and writes this information into the binary so that the device tree loader can then identify the root and go down through the tree. A very important concept is the overlay mechanism. On one hand, you see that if we want to define the tree that goes down, let's say 7 levels, it becomes very difficult to read. This is one aspect. And the other aspect is this modularization, that it is possible to extend nodes that already have been defined in some include file. So the basic idea is that, let me use this again as a pointer. So the basic idea is you start with some node with properties, and then you use the label to start an overlay. And the compiler simply combines all the properties and combines all the subnodes into something that is equivalent to what is written here. So here we have the additional property, the original property without value, and here is an overwritten. It is defined here with the first value, and here with another one. And in this case, the second one will result. This is a very important thing to have this common code for a processor, for example, to have that in an include file. It defines all the basic definitions that are valid for all, let's say, all OMAP3 boards. But in your specific board, you want to override one parameter. Without this mechanism, you would have to copy the full include file, change that one line out of 1000, and to have that, but that's difficult to maintain. With this mechanism, you just make a reference to this value and change just one line. So you describe what is different to the common thing. It could be size of memory, some GPIO that is different, and so on.
Is it possible to do bit operations or something like that? You add something to the original value, set some additional features or bits, or you have to know the original value.
You have to look up the original value and write a new one. So there's no calculation in this. It's just overwriting, just adding a feature bit or something. Yes. So
question in the top level, the label name, and the overwriting has only label. The name, is it optional or what?
No, the name is not changed. The name is the same, because it is put together into a single node. So in fact, one could say the labels are only in the source code. So in the binary there are no labels.
There are the names.
Only the names.
Okay. And the relation between label and name was not clear from you. Okay.
Yeah, the label is for the compiler to support this mechanism.
Okay.
And it's typically, and we will see in the examples, it's up to the device tree programmer how to use it, but typically it's more or less the same text.
When I decompile the device tree, I won't get these
Yes.
labels.
Yeah.
I just get the names.
Okay, just the names, yes. And you will also get the values as hex or decimal values. It is also possible to override nodes. So we can just pick out a subnode by label and have it on the top level of the addition, which is very important, especially for this common code, let's say for the OMAP, that has a deep structure. For example, a single voltage controller in the power management, maybe on the third or fourth level of the root. But with a label, it is just can be addressed here directly. So this makes the device tree quite maintainable. Yeah, you can add subnodes. It is even possible to override it here in this level. So here we have the label, refer to that, and then go here to subnode 2. So there are several options to modify things. We can also overlay the root node, and just we add another slash node. So in that case, the matching goes not by label, but by name. Yeah, the device tree compiler merges that and overlays these additional and overwritten properties into a single binary. Yeah, the include mechanism. There are two different ways of syntax. There's an old one coming from the open firmware, but within Linux it has changed to use the standard C preprocessor. So the DTC in Linux it simply uses a preprocessor to include these things, and this allows also to add macros. But in the macros, you can, of course, use the arithmetic of the preprocessor, but it does not know anything of the code that is going through. Now, the typical thing then looks like include OMAP3, device tree source include, and TWL, the power controller. So you define a device tree for some board and say, well, it's this processor, this power controller. If you have another device with a predefined include, then you include that as well. Yeah, about the node names, they must be unique. There are no two nodes with the same name. Yeah, I do not exactly know which letters are allowed, but the compiler will complain if not. But underscore is allowed, and with the @ sign, it is typically used to separate between nodes of similar function, but where multiple function blocks exist. Very typical is that in a CPU there are multiple GPIO controllers, and there is either a first one or the second one, or sometimes it is simply used the hex address of the where the controller within the hardware, but without virtual memory management, is responding to. This makes it easier to use that information or to debug. If during runtime you can find out what is that name, and from that you can, as a debugging person, read the address and then look if it is the right one. Now about the property values. The value that is used in most cases is an integer value. They are always 32 bits.
What about ARM64?
That's a good question, I don't know. Probably there's a solution, I do not know yet. Okay. You can specify them in decimal or hex. Then strings, they are stored as zero-terminated byte arrays. We can also specify multiple strings. They are simply stored as a sequence of such byte arrays. And what is not visible from here is the API allows to find out how long the full property value is. So it knows, well, here the property starts, and then it can just count the number of zeros to know how many. So here we have a lot of DTS files, DTSI, and so on. So it's quite a long list. It has a lot of devices. And okay, here are OMAP. OMAP 3, Beagle, OMAP 3, GTA04. And here we also see the DTP because I already have compiled that tree. And here you can, for example, see the A3 DTS, A4 DTS, A5 DTS, and always the DTB file.
You compile a link longer than the source.
Yes.
If you include
It
something,
includes a lot of stuff, I guess. Include OMAP, include this.
For example, there is here
How long is the
OMAP.
OMAP 3 file?
There's OMAP 2, OMAP 3. Here's OMAP 3 DTSI, but that's also only a source. It is never compiled standalone. But you also see here that it's a typical size of about 50, 60K bytes for such a device tree. Even the OMAP 4, here the OMAP 4 Panda ES.
The include file must be designed as an include file.
No, that's just a convention that it is called DTSI. You can also include standard DTS files, which is sometimes the right one. Look here, for example, we have the OMAP 5 UEVM DTS, which is for the evaluation board. That comes as it is. And then for the Pyra, we just include this and add our additional things.
Okay.
I can, for example, I can just open that. So here you see the include. So in this case, it's a device tree that is put on top of the existing one, that is tested, that works, but we want to add additional things. So we include what exists. And that is the reuse that was not possible with board files. Okay. Let's go back here. Okay, I have more or less shown you these. So compiling the device tree. Let's go back to the terminal. Okay, here I have a special setup, so it's not just make, I must say this one to start, and there's some setup, and then here it's making the last line. Start making. Okay, now here we don't see much of that. So basically it's here, here this make new image load ashes DTPS. That means make the device trees. So let's go back to the source here and just change something. Here, this node overrides the model property. So we make now something new. If we now compile that again, we have to wait a little. So it's just checking that everything is already compiled. It's linking the kernel, which is independent of the device tree. So here it is now saying DTC, it's recompiling the device trees. And because I have changed this one, it resolves the dependencies because I have here 5 different device tree variants. The difference, just for the detail, the difference of these variants is for different displays. Okay. Okay, I had planned, and we will do that now, to make some, or add some syntax error to that. Let's just remove the semicolon. No, it's not yet compiling. It's okay. Here you see. It says in this file, line 18, there's some syntax error, unable to parse the input tree. That is the good side of the device tree. It tells you about syntax errors. There's one thing to mention, which is not that good with the device tree compared to the board files. For the board files, you also did have syntax errors, which were reported by the C compiler. But it also did report link errors. So if you misspell a property in the device tree, differently from what the driver is expecting, you will not get any error message. With the board file, most of the comparable things to properties have been C variables with a name, and the C linker was able to compare that and said unreferenced symbol. So you could identify such spelling errors a little easier. when I first started to work with a device, I thought, oh well, that's really bad with a device tree. On the other hand, it does not happen very often. And all the other things of the device, they save you so much time that in just this one case, you will find it much faster than ever before. So it's not really a drawback.
Defining constants and including them in both is.
Yes, it's also possible and quite new, and was the main reason to use the C preprocessor now. Okay, that was the right page. No, don't know. Okay, now we have seen how we can change, where we find the device tree, how we can change it, how we can compile it. Now the question is, where do we put it on the device, the binary? We do not need the source, of course. It depends on the U-boot and the boot script, or however it is called. On some other devices, it's unv.txt also. Depends on the booting system. Because the bootloader must, on a device tree system, it must load the U image, the kernel image, which is now constant. All this is really identical for all devices, but it must load a different device tree for each device. On the GJA04, we have developed a concept, and I will explain that, the reasons behind that in a short detour soon. But basically, we have the FAT partition, or usually we have a FAT partition, and there we have the U image, and we just add another file, the device tree binary. Or we can even add several device tree binaries, so well, they just waste about 30 KB or 60 KB on the memory card, but only one of them is used. If you boot from an X partition, it is in /boot.
How stable are these device trees to be expected? So can multiple distributions share one? Is it feasible?
No, the idea is to have one device tree for each device. And the device trees are maintained basically in the kernel tree. using is that I just take all OMAP3, OMAP4, and OMAP5 device tree binaries, put them on my SD card by a single script, so I don't have to care about that. And the other interesting thing is, if all of them are on the SD card, I can just pull out the SD card from the GTA04, put it into the Panda board or into the OMAP5 board. And the same SD card boots, because the kernel is the same and supports all of them, and the device tree, the individual device trees are also on the same SD card, so I can simply switch that. And that's a real benefit, because before I had 10 different SD cards, all written with small labels for which board they are for, and I always got confused. And that is solved now. Okay, now how does the boot process work? On the GTA04 devices, we have a specific U-boot binary. And of course, sometimes a U-boot script. And the logic behind that is that each device has its specific U-boot, because probably it already needs to support different hardware in U-boot. And then it just can load the right device tree for this device. It is loaded into RAM, and the boot M command just gets another parameter with this address in RAM, and then the kernel knows there is a device tree to be loaded, and the process runs. So let me make a small detour about these SD card images. I should think we have time, or
yeah,
we are good in time, so we do not need to skip it because of time. That is an excerpt of a presentation that I had prepared quite a while ago before we started this device tree work. It was about how to migrate the whole system to device tree. Migration concept. It started with some requirements, and it came out that we basically need 3 different system image types. We have called that production image, a single or standard image, and a pure root file system image. The purpose of them is very different. The production image, as the name indicates, is used during the production of such devices to boot them for the first time, to flash the NAND, and to initialize it. But it's not a system intended to be used daily by users. It can be used or downloaded, of course, to reinstall the standard system. If somebody is trying to experiment with the Xloader or U-boot, it's its own variants, it's very good to have a standard system to reinstall. The standard images, they are without bootloader. They assume that the device has in NAND a good and working bootloader, and then you can use the U-boot menu to choose which partition to boot from. And this allows us to have a replicant image for that, a Fujimoko and other images, so you can put multiple images into different partitions and then just to boot which system you would like. The key point is that the kernel is included in that one, but not the boot system. Finally, for the NAND flash, we need a special image, especially because the kernel cannot be included in the NAND root file system. So because there's no FAT partition, there's no X partition, there's a JFFS2 or a UBFS, and the kernel is stored completely separately. So to summarize, or to show that in the picture again, the production image is used for production, for unbricking, upgrading. It comes with a bootloader, U-boot, so that you can boot from the memory card, independently what is inside, boot/boot script. Then the the root file image, it includes the X loader for the NAND, U-boot, and so on. And it has a special kernel and UDFS. And for daily use are the standard images or single partition images or multi-partition. However, it is planned to use different systems. Yeah, because it was about a migration concept, the requirements were that it must be possible to do the upgrade without the RS-232 cable. So the older U-boot, which did not support device tree, should be able to boot at least once for the new one. And it should be possible to downgrade to older bootloaders, but probably it was not really necessary because it worked. Yeah, the same standard image must boot on the different devices, so that the swapping of cards between different hardware works. So the standard image must be universal in a certain sense, so that all these systems can be put into the different devices. That still needs some dynamic configuration. Depending on the device, we need to modify the first stage and second stage bootloader. The kernel must know about the device and to some extent the user file system as well. And I'll go through these aspects. What must be configured dynamically is the display, the touch parameters, for example, rotation of the touch, because that is something which can't be detected by software. Of course, it can be calibrated, but how does the user with a rotated screen go to the calibration? So that must be pre-installed. Boot splash images, the LEDs, how they are used during boot, and the kernel and this interface. Yeah, the U-boot is flashed into the NAND and is only available in this production image. And this, of course, means that for each device variant there is a specific U-boot. Nobody should flash the wrong production image, because then the U-boot is reporting it's a GTA 05, although it's running on a GTA 03. Both don't exist, of course. So it should be the right one. In the kernel, we have the device tree, which helps to do that. It's either in the NAND or in the U image or boot U image. Should be the same for any device. And well, this was the plan. Now it is already done. Therefore, here it's what currently means before it was done. The U-boot did pass a parameter in the boot command line about the multiplexing of the GPIOs, so that it was possible for the kernel to find out on which device it was booted. So that was existing. So it did say multiplex is GTA 04 A3 or B2 or whatever. In the root file system, it is that with configuration, the device should probe not for, or should never, or the root file system should never probe for the device name, or at least try to avoid that. It should check if features are available. If the kernel is presenting, let's say, a touchscreen, if the kernel is presenting an Ethernet interface or not, and should react on that. So the optimal portable root file system has no such dependencies. But unfortunately, that's not possible completely. So for the migration to device tree and device independence, also the root file system needs some configuration. For example, the xorg.conf must hardcode the physical dimensions. Yeah, this touchscreen I mentioned, rotation, pre-calibration, things like UMTS switching on off, how that works. That is currently hard coded. For example, the replicant real driver. Lucas has explained yesterday, there is just a hard code which GPIO is this. This of course breaks this device independence. Yeah, and sometimes this is just done because in a way that the command line, proc CMD line, is read by a script and then analyzed for this multiplexing value. But now with the device tree, I think I can skip that because that's a duplication of what I had explained before. Now, to the solutions. U-boot knows the device it is running on because we have a specific variant for each one. U-boot provides this multiplex variable, and the solution was simply to add another variable, which is called device tree equals, and then the name of the device tree file. The boot script then locates the U image and simply locates this device tree.dtb file. So the boot script itself is again the same for all devices because it has this variable. So this encoding how or which device it is running on is done by U-boot. Okay, this is the final thing. If there's no kernel found on the SD card, then it uses a device tree and NAND for the kernel that is stored in NAND. So let's skip this because it's not yet done. It's about the question how to flash a NAND image using device tree. Okay. So the last thing in this concept, in this migration plan, was a list of things to be done, and the good news is almost everything is done. So U-boot is solved, and we can then go back to the kernel device tree. Yeah, the U-boot provides this variable. The boot script looks up the location and using the name of the device tree. It uses it, provides it. Yeah, you can go through that in the online slides when they are presented. So the only thing that is missing to have a full system is booting a 3.18 kernel from NAND. And doing that means to flash the 3.18 kernel and the device tree for that specific file into the NAND and make that all work. I think it's not a difficult step, it just has not been done. And before we don't have a really stable 3.18 kernel, well, that's not the most important thing. Okay, so adapting the flashing scripts to NAND flashing, that's missing. Now, back to the device tree. Well, we have learned how the syntax is, how it is on the device, but the key question is still open. How do I use that? I have now the tools, but what do I do with them if I have a specific target in mind? I want to solve a problem. I do not want to learn, I want to solve a problem. And filling this gap, that's the next slides about. How do I know what I should write into that device tree? And what does it mean to Linux drivers? The solution is another concept, that is the bindings. The kernel has in the documentation, it describes the so-called bindings. And bindings means a specific driver, let's say the driver for the touchscreen. It has a document, the bindings document that says, well, this driver has this parameter for rotation, this for the dimension of the touch, and so on. And this is described in these bindings. So let's just look into that. That was the wrong one. This one. Here we are on the GTA04. So you see it's a 3.18 RC5 for GTA04. Ah, no, that's wrong. We must look into the kernel code, of course. Bindings is here. Okay, here we are on the master tree. Documentation, device tree, bindings. Okay, here the bindings, you see there are some text documents and a lot of directories. So the structure of the bindings almost resembles the kernel tree. If we look for the touch screen, it's an input driver, so we have to go to this input. Ah, okay, here down there's some touch screen. Okay, and our chip is the TSC2007. So we look into that. Oops. Okay, it's the bindings for the Texas Instruments TSC2007 touchscreen controller. It says there are required properties with compatible entry, and I will explain later what it really is, this magic. It needs an entry called reg, which is the I2C address of the chip, which is treated similar to a set of registers. Then there is X-plate ohms, which is the decimal value, how many ohms the touchscreen resistance typically is. This is needed by the driver for its internal calculations. There are optional properties. For example, there can be a GPIO for interrupts, so that it can detect the pen interrupt. But the driver is written in a way that it also works if there's no interrupt, but then it has to constantly pull the I2C, which draws more power and so on. But defining the GPIO is the means how we describe hardware. We can say, well, this board has connected this TSC chip with this I2C, with this interrupt. Interrupt parent interrupts, that's additional information for that. Then we have this swap X and Y, which just mixes the coordinates. That is can happen if the PCB layout has done in a way to optimize that although the chip documentation says this is the input X and this is the input Y, they have been swapped in hardware, and here we can tell the Linux kernel driver that it has been swapped, and we will just reverse that. So there are additional things. Here are some references, and also there's an example. For example, here, this driver is on this example board. It's connected to an I2C1 bus, the number 1. And you see by this reference, by this label, how that overwriting works. There is already a node for I2C1, which defines all the other devices. But then there's one entry which adds the touchscreen controller. The name of the node is add49. This is just more convention to use the real I2C address here. And then here are the entries as defined by the bindings. Also see here this example, here interrupts, that's an array of 2 values, or here this GPIO is defined as a mixture of such a P handle and 2 integers. While this here is just a single value.
Would it change if the brackets weren't there?
Sometimes yes, sometimes no. Here in this case, with 2 entries, they are mandatory because it has a completely different meaning. Here, I'm not sure when it makes a difference. I think it depends on, one would have to study if the open firmware API in the kernel can convert that without a single value with or without brackets into the same result, or if it complains. If it complains, you will get it in the boot log. It may say
I would
property
guess-
unreadable or wrong format or something.
This is an array, and they, no, I don't know. The length should be coded there, or
Yes, the length of an array is known, so, but I don't exactly can tell is if how the encoding in the binary works. I have not found a good document for describing how a flattened device tree is
it's
built.
all about do it the same as it done before.
Yes, yes, that's
Can you scroll up the definition?
yes.
So, this is, for example, the others just show values default to 0, where I have to expect that min y is not 0, but 0 in angle brackets. Even if it's a single integer value like the ohms.
Yes, I think it should be in
Somehow you have to
Brackets,
define
yeah.
types, then if it's
Yeah,
an array
yeah,
or
yeah.
if it's a scalar, then
That's a good question.
or is it
I have
just
not
equivalent?
talked deeply about that. When you
It
need
could be
this,
just a list of integers,
Yeah.
then it should be integers and only
the
the
question
compiler
is
knows the
a
length.
single integer is the same as a list with one entry. Yeah, I do not know if it's treated the same. Marek, do you probably know by? No. So something for more research. Okay.
If the example says angle brackets, do angle brackets.
Yes. That's, yeah.
What happens if?
The answer is 42.
As always. Okay. That was an example. Now, let me tell something about this magic compatible property. It's always mentioned, yeah, you have to make that compatible, but what really does it mean? There's some hen and egg problem. The device trees wants to define data for drivers. But these drivers, do they exist in the kernel? Are they loaded? And in the other way around, the drivers want to know specific data. So this compatible property is used to describe that a specific node is relevant for a driver, so that a driver can ask, oh, what are my important device tree nodes? And on the other hand, the driver loading and probing mechanism is using the compatible entry to locate the drivers. So many drivers usually need this module alias entry or something similar. There are variants in their source code so that they can really be found. They also need a compatible table, which I have forgot to add as a bullet point. And finally, the association of this driver with some compatible entry is stored in the debmod or modprobe-c database. So you can go through the modprobe-c, then do an fgrep or grep to look about this additional information, which does not exist or is not needed for non-device tree things. So the result is that a driver can support different compatible variants. For example, let's say an E2C, an E2 prom is almost the same, but different chips have different capacity. So there can be compatible entries in the driver saying, well, this driver is compatible for a 2K or 4K and other sizes of the same, of almost the same chip. And then in the device tree, we tell this exact chip name. We say this board is compatible to this chip variant, and then this matching finds out that this board needs the driver, which could support others, but in this specific case, it has this capacity. Then it is used by drivers to locate their default node. So a driver, if it is probed, already gets a pointer to that node, so you don't have to care much about standard drivers. If you write a driver for your device and make it device tree compatible, there's a special variant of the probe function which already brings in your the device tree node that you define for that. And finally, a node can be compatible to multiple drivers, which is the reverse of the above. This is usually used for the root node. The root node is compatible to several components on the full system, for example, the power controller and the CPU, or for CPU stuff or system on chip stuff. The driver, a node describes components that are handled by multiple drivers. So this compatible is matching drivers with the nodes. Yeah, another example, we already did look at the TSC driver here. This is really from the GTA04. We have the pressure sensor, the BMP, and it's also an I2C driver. We have here compatible, define the register, interrupt parent. So in fact the comment is not correct. It's not could enable, it is enabled. So interrupts 17, and here you see one of the C macros constants. This here IRQ type edge rising. That's some define in a source file that is shared between the kernel code and the device tree. So this constant is only defined once and keeps things in sync. I already had mentioned these P handles. Sometimes drivers need access to other drivers or other devices. This can be done by these P handles. Examples are regulators. The regulator has its own device tree node, but someone is using the regulator and then can make a cross-reference to that. But in the device tree, it's the P handle. It just describes a relation. In the kernel, this becomes a real address of a data structure where the kernel driver that uses the regulator then can call functions from the regulator framework. GPIO controllers are very often used. Example, some physical interfaces, for example, for USB or other high-speed interfaces, they also use that heavily. Parameters used in combination with the P handles depend a little on the system. For example, for GPIOs, you usually specify the GPIO controller and the number of the GPIO in this controller. On the OMAP3, there's a third parameter describing if it is an active high or active low GPIO. The proposal how to handle that in practice is, my proposal is just look at comparable examples then inside, outside the kernel tree. Outside the kernel tree means Google. Find examples for the chip you want to interface, and then I think it's learning by examples. How does an example look like? Here we have the compass chip of the GTA04, HMC and type number, address 1E hex, the Honeywell, and it has a property VDD supply, which then is a P handle to the auxiliary regulator number 2. Now the node for that is defined somewhere in the OMAP3 include. There is somewhere down the root, there is some node defining the regulator internally. There it will define which register addresses are used to control the controller, but we don't see it because we do not even need to see it. What we here override are three parameters. We define the microvolts minimum and maximum of the regulator, and here we say always on. This is for some hardware reasons specific for the GTA04 board, that it should never be turned off. So we specify it just here, and here in the third line of the magnetometer or compass, we define the relation. And then the magnetometer driver knows about that regulator. It can test if it is really available, if it's turned on, if the voltage is okay, whatever the driver wants to do. So, understanding examples, let's go again into some source code. Okay, let's go back here on the bindings. Yeah, okay. Let's look into in here into the GTA04 device tree so that you get an overview or indication what is inside there. We have decided to base it or to make the base definition for the GTA04 version A4, because that is the one that is most distributed. Then we include the OMAP3XX DTSI, which defines this specific CPU. Then we use the root node. Well, we just copy the compatible entry. Here define some CPUs, memory. This is, for example, something which cannot be defined here, because the OMAP is only the processor. It does not know how much memory is connected. How much memory is connected is board specific. But for the GTA04 boards, we always have this 512 megabyte memory chip.
And once you do a board with more memory, you can write a second one and override that value.
Exactly. You just override this entry. Then there are some aliases. Aliases is a mechanism that is sometimes used in the kernel or by kernel drivers in addition to the P handles. And here for the display system, it wants to see aliases. Then, okay, that would be for is the OMAP3 ISP, which is a camera interface within the OMAP that is working, but there's no compatible, or it's not working because there's no compatible driver. It looks as if this could be the right definition because we have not yet found the final bindings document. My hope is because I have seen that something was submitted for this driver on the kernel mailing list that it will appear in several weeks. So there might come up a driver for that. So this is a case where we already have something in the device tree where the driver is missing. So it's more the documentation of how our idea is looking like, and then we have to fix it as soon as the driver comes. But it is simply ignored by the existing kernel. Yeah, here, let's go to this. This is a quite simple but very important thing. It's the GPIO keys entry. It's compatible to the GPIO keys driver. And it has here the GPIO number 7 of the first GPIO controller, which is active high. Yeah, and the driver generates, if that line goes high, it generates an input event with the code 169. And this is the auxiliary or user button. So here we have defined the user button is connected to this specific GPIO and generates this code.
And the label aux means that if I somewhere want to redefine it, I just write label aux and Linux code.
In that case, it must have been a label here. So we would have here aux button this way. So this type of label is within the device tree data. So a driver can use that label if it wants. It can read is there a label property, and if yes, for example, use it in debugging or.
Okay. It's just a property.
Just a property. The property, like all others, a string property. And another interesting thing is defined here. That's a property without a value. Pure existence is stated here. It's a wake up, which means that if the system is going to suspend, this driver will register this GPIO for wake up. So adding such things, which are very important for a smartphone, a portable device, has become really easy. Doing this wake up thing in the board file would have nothing to do with this driver. It would have needed a different mechanism. Yeah, here we use the GPIO keys driver for the wake up from an incoming phone call or an incoming SMS. Yeah, here just some more examples. This is a physical driver for the internal USB. It's not much which has to be defined. Antenna detect is for the GPS antenna. That's an XCON, external connector driver with GPIO. This one also has a label, and in this case the label is used so that a special sysfs node is created using this label. But that's logic implemented in the driver.
But it's a property, and how it's used, it's...
Yes.
The debounce delay and the interrupt.
That's also defined by the driver.
So the interrupt comes 10 milliseconds later.
It means that it makes a debounce delay, then checks the GPIO again and
throws it there.
Yeah.
Okay.
Well, in this case, it uses, no, it does not throw an interrupt.
It uses the interrupt.
It uses the interrupt of this GPIO. If you plug it in, it gives an interrupt when you unplug. And it uses a debounce delay to check if that was a spurious thing or not. And it has a state on and state off. Those are two strings, and then in the sysfs you can cat sys class XCON GPS antenna state, and it either says external or internal. Then we have here definition for the sound card, various codecs. Unfortunately, here the drivers behind that do not work as expected. Here's, for example, the hardware monitor, which is used to detect battery voltage or some other things. Or battery, there's a fallback battery driver. If the HDQ or one-wire interface into the battery is not working, we still have voltage values. Here, this is a more complex thing. You see there are subnodes. This is a SPI LCD, the LCD definition. It defines that it is controlled by an SPI interface. We have used the GPIO SPI, have defined the GPIOs. Then we have defined the panel that is controlled by that SPI, which is the panel of the GPIO4. And finally, this panel defines ports, which is a logical port. And finally, here it makes a reference to something deep in the video system, so that this rather lengthy entry describes exactly how the GPIO4 hardware is connected and how it should be logically used so that we have a video out.
But the resulting thing is not a software SPI, it's a hardware SPI.
It's for GPIOs going through wires and the display as a hardware SPI.
It's a bit banging driver.
Bit banging driver.
Yeah,
A bit banging driver.
Yes, yes.
That's software SPI.
Yes.
Okay. With a frequency of 100 kilohertz.
Yes, maximum. Well, it's only for the display. It's only used during initialization.
Ah, okay.
It's only used once, and then
Then it's okay.
Yeah.
Then bit bang
Then
is
it's
used.
yeah, more than sufficient. Okay, what else do we have? Something about backlight. Sometimes there's a workaround. Here we have a TV connector, the TV out, which is also something a little lengthy. Then we have for Bluetooth, the GPS driver, which is mainly GPS power on-off. Modem on-off. Okay, and this is something more internal. It's similar to the pin multiplex in the OMAP. There's a device control, system control register. Then something I have not yet mentioned is the pin multiplexing. Usually these processors do not have enough connections for everything. So the silicon designers, they decide, okay, we make a pin multiplex solution so that the system designer can finally decide which function he wants to have where. And this, of course, must also be controlled during boot time. So, and sometimes before going to suspend and waking up, it's sometimes necessary to reprogram this pin multiplexing for optimal power saving. And this is defined by entries in the pin multiplexing area. There's a driver behind that. There's also a compatible entry, but we don't see that because this PMX core is already defined in the OMAP3 device tree. So we just have to define, for example, here for an UART1, that these pins have to go to a specific multiplex mode. Here we have multiplex mode.
Several overrides for the same thing. Are they the last one wins? Or?
Here, the kernel detects during boot that there's a duplicate and reports that. But I don't know if the last one wins or the first one. Either one wins.
So there will be a message every time.
Yes. Yes, you will notice that during debugging, and then you should not have that because there should only be one, should be static. There is a special mechanism which can be probably be seen here, because here you have a duplicate, but these are different node names. So not both of them are active at the same time. So it is possible to define two different sets of multiplexing and then have the driver switch between that. And here for this is logic used for the GPS of our GTA04, and that needs this mechanism of switching. Unfortunately, this is one of the areas where the kernel maintainer said, oh, no, we do not like yet. But we don't know another solution. Okay, there's a lot of pin multiplexing. Here, for example, this is the battery of the parallel interface to the display. Yeah. Then I2C, backlight.
What would
and
be
so on.
the best thing if you say, okay, I have the OMAP and I have pin multiplexing, and it's I need to override the property, and I have double definition. So what would be the thing to solve that? Making it your own device tree?
You can override the node, the complete node. You
Okay.
can replace that. That is one mechanism. Or you can modify one level deeper. Or you can. What else can
Just
you do?
override that node which originally had been multiplexing in your cookie, and
But you need all the multiplexing data to override that.
Depends on the structure, how that is structured.
Ah, okay.
For example, if you Yeah, it's a little difficult. Let's make an example. On your device, this one does not work, and you have removed the chip. So you have the pin. So you have a GPIO 1113. You have a spare pin, and you solder a cable. Want to use that for something else?
Yes, of course.
Yeah. Then you can look if this line is already the right one. If it is, then you have nothing to do. You just use that interrupt, but you have to disable the BMP driver. That can be done quite easily by overwriting the compatible entry of the driver and make it compatible equals nothing. Then the device tree says, well, we need a driver called nothing, but that does not exist, so it is not loaded. So with that way, you can remove a driver. The pinbox, if it is okay, then no problem. If you, for example, want to make that an output, you would use this label and just overwrite this. Then the device tree compiler would remove this entry completely and replace it with a new one.
Okay.
Is it possible to specify an empty list? Pin control single pin spotlight empty list? Or do I have to get another spare pin for that to override it?
It could be possible to make it empty.
Or make it 0 or whatever.
Yeah, it depends on what you want to achieve. Sometimes it's
I just
solution.
want to get rid of
I think we have
allocations
one case where
or none or nothing.
yeah, where a 0 is used as a GPIO controller, which means no controller. Okay. So and there's
And then it's free again. Can you reuse it?
Yeah. So here we have more about the I2C1. That is a backup battery charger configuration and so on. Auxiliary voltages. Okay, here in the end, here we have the touch screen. Ah, yeah, okay, here we have the minimum, maximum with square brackets. Okay. I think you have seen a lot of things, of examples. This is in the GTAO4 device tree file and is usually the starting point to look in when making something new. Before I forget, I wanted to show one thing. We have an A3.dts just to show you the how differences between device variants are managed. Here for the A3 board, we include the standard, then just define a different or the same model name. No, it's a little different here. It says A3. Here we have that case. I found it. We say the on-off GPIO for the modem is just a 0, which means it does not exist because this definition has a standard GPIO for turning the modem on and off. But the A3 board is missing that function completely because it was an older one, this was a bug that was solved later. Okay, and here the one GPIO, this for the wake up, is a different one from the A4 board. Now the A4 itself is very short because it is the basic include, and the A5 is prepared but does not yet exist. Okay, it has here a small change again. Here it's A5. It is planned to have a GPIO for the headset jack detection, so that is already planned to be here. And here the modem has been, the modem on-off indicator has been moved to a different GPIO. So you can see probably that it was a large work to make the GTL4 work at all, but these variants are very small. Okay, more to come to an end, I have prepared a very small project for the GTA04, but we will not do it in completion. But just to recapitulate the idea how to progress. The idea is that here this RS-232 cable has a DTR, device terminal ready, I think it is called. But that is not used. It's not controlled, it's not used, but the hardware is there. So for completeness at least, we should describe that in the device tree. It's related to the UART3, and if we completely implement that, then we can use from user space the STTY CDTR DSR command, or there are some I/O controls to handle this. So how would we do that? The step 0, I have called it, is, which goes into some question that already arrived. Do we write a new DTS driver? Do I want to have a variant that supports that? Or do we overwrite the existing, creating some patch? Since this is a quite general function that is available on all GTA04 boards, it's probably the best to just modify or to write a patch for the standard device tree. What we need to do is we have to set the pinmux of this GPIO. We have seen that it is done by a pin control single entry, which does not yet exist.
One question here is, the pinmux are also defined in the U-boot.
Yes.
So when do we set up then in kernel, and when do we set up then only in U-boot?
Yeah, that's something you have to decide yourself. The general rule is that the kernel should define all GPIOs that it needs, for which a driver exists, in the way the driver expects them. This should be the same as U-boot already has done.
It could happen that U-boot is not involved in booting, then if it's missing the
Yeah.
kernel driver.
Yeah, that is an additional aspect, yeah. So let's say in these words, the device tree should not assume that any pinmux is already defined by somebody else. And U-boot defines those that it needs. The kernel driver defines others that it needs. And everyone is doing it in their way. And if the system design is good, then there is no difference. And to make it more complex, there are default pinmux settings of the processor after reset.
Basically, U-boot will write what it thinks it's good, and then after that, the kernel writes what it thinks it's good. And if you got problems, deal with it.
Yeah, exactly. So now we have really to dig into 3,600 pages of the OMAP3 technical reference manual, because we must search for the GPIO21. I've prepared that a little so that I already have it opened. Here it is, 3,600 pages. But it's not difficult in this case to find something. We just type GPIO21. Oh, we have to use it without underscore.
Where is it?
It's gone. It's lost.
Lost in translation.
Maybe take some time.
Yeah, sometimes it may.
It's just space.
Yeah, you're right. Good idea. So, and we are here in the control module. Let's make it bigger and remove this, because first hit was already in the right area. So the control module pad configuration register fields is a long table of all these pin multiplexing registers. And here you can see the registers are called padconf something. Here's the address, for example. And depending on the mode that is written, there's a different function on that. And now we just have to go here until we find the 21. It's not sorted by sequence. So
Are you sure that it's 21?
yes,
Because the underscore was right and it didn't find it.
yeah.
Are you in the right document, or are you on
That could be. It could have been wrong. DM.
Looks right.
Or ist nicht das OWeb irgendwas TRM? OWeb 5?
Ja, ist
das hier weißt du doch auch TRM.
Ja.
Dann weiß ich nicht.
It's
Wikimedia muss setzen.
it's a DM37X multimedia device. And last time I searched it was found. Yeah, now it's found. So, okay, much better, much easier. So, okay, here is basically here we have now the information that the GPIO21 is mode 4 and it's controlled in this register at this address. And there's one additional thing which is very important for this pin multiplexing. There are always 2 pins controlled by one register. So we have, if there is 31.:16, then we have to add 2 to this address. This is the hard address in the physical address space of the CPU. And fortunately, the device tree is handling that quite directly. So let's go back to this. I already had copied this line. So we see the address 25E8, and we have to add 2 if it says 31:15. So we have to remember this.
16, obviously.
Yes. Let's change it immediately before we forget. So we have to remember this OX25EA. Another thing we have to keep in mind that OMAP has different PinMux controllers, and this is the PinMux controller number 2. And multiplex mode 4 is GPIO mode. Mode 1 would make it a SPI interface.
To be very picky, you have to think about changing this register may affect the other half. So there will be a read modify write. And if you interrupt it within, you can if you only do this during initialization, it should be okay. On the
But
fly.
I think the driver is locked against.
Okay.
Yeah.
Then it's okay.
Yeah. It's
Static initialization.
yes, and it's static.
If it's only initialization, I
If
don't
the
have a problem.
data and the PinMux driver takes care of the situation. But you're right.
Hope so.
So the result looks like this. We need a OMAP PinMux Core 2 because it's the second controller. There's already a node for the there's a new node for the UR3 DTS pins. We make this pin control single pins. Then we use a macro, which is also specific to the Core 2 PinMux. And there we use the address 25EA, say pin output, MUX mode 4, and this should switch this pin to output so that we can use it. Okay, this was the PinMux thing.
Where can we see that it's core number 2?
Okay, that comes
Because I
from the
think it's not
TRM. In the TRM, there's specified if it is core 1 or core 2.
In the table?
No, there are 2 tables, two different tables.
Okay.
And the other thing is, that's it. You can also recognize that this 2.5 address is different than the 2.0 or 2.1. From the address, you get a hint But if you use the wrong macro, then you will end up in a completely wrong entry, and it might write to a wrong register and modify some.
It will.
If it does not exist, it gives a core dump.
At least it tries.
Okay, so now we are almost done. We are almost done. The step 2 is we have to add this new GPIO to the UR3 driver. The UR3 node already exists, and fortunately we have in our kernel, we already have a driver that can drive a GPIO as a DTR. It's not used yet for the UR3, so we just add this GPIO. GPIO 21 is the port 21 of the GPIO controller number 1. And we remember that GPIOs have to be defined by 3 cells. So the code should look like this. We override UR3 node and add just the link to the DTR GPIO. Here it is written GPIO active high. I have not checked if high or low is the right polarity. It depends on the circuits behind that. That's probably something that will become obvious during testing. Yeah, testing, for really testing that, we would need more equipment because it's RS-232 and a rarely used interface where it is difficult to test it without an oscilloscope.
It's a slow signal, so simple voltmeter.
Yes, you could, but then we have to find out which pin it is here, and since this is the console at the same time, we have to open the connect and so on. So I decided, well, we will not test it here in the group, but we will test that after this workshop, of course, and if it works, it will become part of the next kernel.
If you think to put that in your kernel, in your ETS, there was DTS pins, not DTR pins.
Ah, okay.
That's pretty good. So
pins.
one slide, 4 or 2 slides? Yeah. You have 3 DTS
Ah,
pins.
okay. Yeah, thanks. Well, that wouldn't have changed the logic, but
but then
but readability
yeah.
and consistency.
If you look for DTR, you won't get that spot in.
Okay, so the final words is about what about the device tree on other systems. There is at least one project I know that uses a device tree on a non-Linux kernel. It uses a Darwin kernel, which is an open source kernel of the macOS. And there's a project, Darwin on ARM, and it did run obviously on the BeagleBoard XM and the N900. And you can go to the web and look into their device tree. So this is the device trees. Obviously, he has here 1, 2, 3 directories, and here has the Nokia. The RX51 is their internal name, N900 the official. Yeah, how does it look like? He uses some includes based on the Linux one. Well, that's good, but he did obviously have to modify some things. But the GPIO keys, it looks quite similar. GPIO is the same, but here he has things that are not really comparable to Linux. On the BeagleBoard, it's much smaller. It just defines this compatible to the CPU and ARM, Apple ARM, and the memory. But the principle is the same, and it could be possible to mix both, to have a device tree for a BeagleBoard that runs both or supports both. Okay, so that's, I think, everything I know about device tree. Everything beyond that, we have all the same questions to some more experts. So any comments, other questions?
So that device tree file I just can't copy on the U things. I have to look for the U stuff again and for the boot configuration.
Yes.
It's similar, but they have their own source code.
Yeah, they have their own boot system. Okay, then.
Does it also do some kind like dependencies? The drivers might not necessarily deal about themselves. For example, the driver needs to be powered, or the device needs to be powered. Can it also define in the device tree if the device driver does not actually say, doesn't actually know that it has a special power source?
Usually the drivers have some power properties. I think the example I had shown with the magnetometer, it has a VDD supply entry, and most drivers have that. So there you can specify a regulator that powers the device that is controlled by that. And if you define that, it's one line in the probe function of the driver to fetch this regulator and to enable it. So my proposal is just look into an example that is using that and how it is coded in the driver. Okay, then let's make a break.